following limit. So part A, we've got the limit as x approaches 2 of 3 times f of x minus 2 times g of x over f of x. Part B, again, we'll do the limit as x approaches 2 of f of x times g of x. Let's do part A here first. For the limit laws, maybe we'll go through this one in bits and pieces. If you have a limit of a fraction, it basically says you can take the limit of the numerator over the limit as x approaches 2 of the denominator. Okay, well, there's also some more rules that say, okay, if you have addition and subtraction, it says you can look at the limit individually. So we'll have the limit as x approaches 2 of 3 times f of x minus the limit as x approaches 2 of 2 times g of x. Again, in the denominator, I'm going to write it a little closer. We've got the limit as x approaches 2 of our function, f of x. Another one of the limit laws simply says if you have constants being multiplied by your function, you can factor those out. So we have 3 times the limit as x approaches 2 of the function f of x, minus, I'm going to pull the 2 out front, 2 times the limit as x approaches 2 of g of x. Well, again, all of that is over the limit as x approaches 2 of f of x. And now we're in a position to start plugging in the given values. So the moral of the story is you can basically just plug things in. A lot of people, very few people write all this stuff out when doing limits. So let's see, we set the limit as x approaches 2 of f of x. That was given to us as 4. So I'm just going to plug that in. So we'll have 3 times 4 minus 2 times, well, when we do the limit as x approaches 2 of g of x, we set the limit as x approaches 2 of g of x is just negative 5. So let me plug that in there as well. And again, we just said the limit as x approaches 2 of f of x. That's giving us the value 4. And now we're in business. We can just do our arithmetic. So 3 times 4 is 12. Negative 2 and negative 5 is positive 10. All over 4. Let's see, that's 22 over 4, which we could reduce. We could make that 11 over 2, or I guess that's what, 5.5. So that would be our limit, the answer to the limit question in part A. All right, so just another problem here related to the limit laws. So in part B here, we'll just calculate our other limit, which was the limit as x approaches 2 of f of x times g of x plus g of x. And basically we're going to do just the exact same thing as in the first part. So again, I'm going to write out the steps. It says really we could take the limit as x approaches 2 of the first part, f of x times g of x, plus the limit as x approaches 2 of g of x. So it's kind of like you're distributing the limit. And then there's another rule that says if you have a limit of a product, you can look at those individually. So we would have the limit as x approaches 2 of f of x, all of that times the limit as x approaches 2 of g of x, plus the limit as x approaches 2 of g of x. And again, all of these values were given to us at the very beginning of the problem, so now we'll just plug all of these in. So it says the limit as x approaches 2 of f of x, that equals 4. The limit as x approaches 2 of g of x, we said that was negative 5. So let me just plug negative 5 in to both places. Well, 4 times negative 5 is negative 20, plus a negative 5 or minus 5 will simply give us negative 25, and that will be our value of the second limit. All right, in this video I want to look at a little bit more of the limit laws, and this is kind of an important little result. It says if you have a function that's continuous at some number a, it says, well, then the limit as x approaches a of the function equals f of a. So really what this says is, it says if you have a continuous function to evaluate a limit, just plug in the numbers. That's all you got to do. So we can go through these, in fact, pretty quickly. So if you look at the limit as x approaches 1 of 3x plus 5 over x plus 4, if you think about the function 3x plus 5 over x plus 4, this is a rational function. The only place where they're not continuous is where they're undefined. Well, this is going to be undefined at negative 4, but that's not where we're doing the limit. So it says, well, to evaluate this limit, all we have to do is just simply plug in x equals 1 everywhere that we have an x. So we would get 3 times 1 plus 5 over 1 plus 4. Well, that's going to be 3 plus 5 or 8 over 5, and that would be the answer to our limit. So to me, basically, it seems like most calculus problems when you see limits, remember it's bad to divide by 0. So as long as you're not dividing by 0, plug it in, and whatever you get, that's typically going to be your answer. Okay, so again, that's not true in general, but most of the functions that you see in a calculus course are going to be continuous functions. Okay, so same thing with the next problem. If you think about x squared plus x minus 6, that's just a parabola that's opening upwards. Well, parabolas are continuous everywhere. Well, in particular, it would be continuous at 0. So I'm just going to plug 0 in. So I would get, well, 0 squared plus 0 minus 6, or it says you would just be left with negative 6 as your solution. Okay, so here we've got x plus the square root of x plus 11. And if you think about the function y equals x, that's a nice continuous function. Square root of x plus 11, that's just actually a square root that's been moved over a little bit to the left. Well, there's a rule that says if you add two continuous functions, it stays continuous. And so again, all we're going to do is just plug in the number 14. So we'll get 14 plus the square root of 14 plus 11. Well, that's going to be 14 plus the square root of 25. Well, the square root of 25 just equals 5. So we get 14 plus 5, or the value to our third limit here would simply just be the value 19. Alright, in this video, I'm just going to talk a little bit about one-sided limits and a few different problems here. Probably what I'll try to do is make some sense out of it by graphing, but then also we'll just kind of talk about how you would do it algebraically. To try to have it, how you would evaluate one of these limits, say, without resorting to graphing, but just to get some intuition. So let's look at part A here first. We've got a little piecewise function. So we've got the function f of x is going to be x plus 3 if x is less than or equal to 1, and then we've got x squared minus 2x if x is greater than 1. And we want to figure out the limit as x approaches 1 from the left. Okay, so notice the little minus sign is kind of to the right and above. So what that means is we're coming from the left of our function. So, okay, well, we could graph this. Do a little rough sketch here. So if you think about y equals x plus 3, well, that's just going to be a line with a y-intercept of 3 and a slope of 1. So, but notice it only looks like that for x less than or equal to 1. So if we plug in x equals 1, we would get the y value of 4. Okay, so there's going to be a point at 1, 4. Again, normally the line would just go on forever and ever and ever, but in this case, well, it's only valid for x coordinates less than or equal to 1. So we're only going to get the left half of this nice little line. Likewise, you can think about graphing y equals x squared minus 2x. Well, to graph this one, you could always maybe start plotting points. Notice if you plug 1 in, you would get 1 squared minus 2 times 1, which would be 1 minus 2, or negative 1. So there's negative 1. But since it's only valid for x strictly greater than 1, we're going to put a little open circle there. We can also think about finding the vertex if you want to just make sure that your graph is really nice. So remember to find the vertex of a parabola, we can use the formula negative b over 2a. So just to remind you of a few little algebra things here. So negative b over 2a, in this case, it says we would take the negative, and again, b is whatever the coefficient on the x term is. So we would get negative 2 all over 2 times a. So in this case, a would be the coefficient in front of x squared, which is 1. So we would get 2 over 2, or positive 1. So actually, at the x coordinate of 1, we are finding our vertex. Since x squared is positive, we know that it's going to open upwards. So we'll just make it open upwards. But again, it only looks like the parabola for x coordinates greater than 1. So I'm going to make it, just basically the right side of the parabola. All right, so now we've got a nice little picture. Again, there's our function f of x. Again, this is kind of overkill to do the problem, I think. But again, it's important to get some conceptual idea of what's going on here at the beginning. So, and I think a picture, as they say, is worth 1,000 words. So we're looking at the limit as x approaches 1 from the left of our function. So again, from the left is what the little minus sign indicates. Okay, well, so here's the x coordinate of 1. Well, if I'm coming in from the left, that means I'm taking x coordinates smaller, just a little smaller than 1. Well, if I take x values that are just a little bit smaller than 1, if I plug them into my function, or equivalently, I can think about the y values on the graph. Plug numbers just a little bit smaller than 1 in, well, what's going to happen to the y values? It looks to me like the y values are going to get closer and closer and closer to 4. Again, take x coordinates a little bit smaller than 1, you're going to get y values that could get closer and closer to 4, and that's going to be our solution. We would say the limit as x approaches 1 from the left of our function simply equals 4. That's all there is to it. Algebraically, what I would do, to just do this, as in the previous video, we said if your functions are continuous at the point, you can just plug it in. Well, this isn't quite continuous at x equals 1 because it breaks. But again, you can still basically plug it in. So if I look at numbers, okay, so 1 from the left, again, that number's a little bit smaller than 1. Well, okay, so should I use the first formula, x plus 3, or the second formula, x squared minus 2x? Well, if I'm using x coordinates that are a little bit smaller than 1, that would be x less than or equal to 1, then I should just use the first formula. So equivalently, I could say the limit as x approaches 1 from the left of our function. It says that would be the limit as x approaches 1 from the left of the x plus 3. Now, if we simply plug in the number 1, we'll get 1 plus 3, or we'll get the answer 4. So again, the same way to get the answer. Again, I think it's nice to have a little picture to go with it. Suppose, so the question didn't ask this, but suppose we were asked what's the limit as x approaches 1 from the right. Well, if we do 1 from the right, now, okay, I'm taking x coordinates a little bit bigger than 1. Okay, so if I use x coordinates a little bit bigger than 1, now I'm kind of sitting on the graph of the parabola. And as x gets closer and closer to 1 from the right, the y coordinates are getting closer and closer and closer to negative 1. They never actually hit negative 1, but they get arbitrarily close to it. So we would say the limit as x approaches 1 from the right equals negative 1. If the question had said what's the limit as x approaches 1, and they didn't specify from the left or the right, recall the limit from the left side has to equal the limit from the right side at a point for the limit to exist. And since we're getting different values, negative 1 and 4, we would simply say the limit as x approaches 1. In this case, it does not exist. Okay, so just to illustrate again graphically what's going on, algebraically what's going on, so certainly left-hand or right-hand limits can exist, but the limit itself may not exist. So, all right, I hope this example makes some sense. I'm going to sketch the other ones as well, and again, just try to talk about how you can just, also use the formula, because eventually, this is really what you want to do, right? You don't want to have to sketch out every single graph every single time. Be much too complicated and much too time-consuming. All right, so another example here related to one-sided limits, and in this case, we're going to do part B. We're going to look at the limit as x approaches negative 4 from the left. It's kind of hard to see my little minus sign there, of the function g of x, where g of x is the absolute value of x plus 4. So, two things again. I'm just going to sketch the graph. So just to remind you some algebra stuff. Remember, so x-axis, y-axis. Remember, absolute value of x just kind of looks like a nice little v. If we replace the x with x plus 4, remember, that shifts the graph, and does it shift it up, down, left, or right, or it does something? Well, you can always start plotting points if you're not sure. It turns out it's going to shift it 4 units to the left. Okay, so there's the absolute value of x plus 4. And again, that makes sense, right? If you plug negative 4 in, you're going to get 0 out. So that's how I used to always even remind myself, you can always plot points, so plot points if you need to. Okay, so we're looking at this bottom graph, and we're thinking, okay, what's the limit as x approaches